When we have solutions where there's a specific set of allowed values of a parameter, here energy, that are required for the solutions, we can call those allowed values the eigenvalues of the problem. And associated with these eigenvalues, there are also particular functions, and we call those functions then the eigenfunctions. And the totality of these eigenvalues and eigenfunctions we could call the eigensolutions. So here are the eigenvalues here, these energies En, and here are the eigenfunctions. Here, since the parameter in question in the eigenvalues is an energy, then we might call these specific eigenvalues eigenenergies, and that's quite a common notation in quantum mechanics. And we can refer to the corresponding eigenfunctions then, since this is an energy problem, as energy eigenfunctions. Incidentally, there's another concept that we have not quite come across yet, but we might as well introduce it at this point because it will come up soon enough, which is the idea of what's called degeneracy. In some problems, though not the one we're currently looking at, it can be possible to have more than one eigenfunction corresponding to the same eigenvalue. That phenomenon, if it happens, is called degeneracy. Now, this is perhaps unfortunate because degeneracy is used for many other concepts in science and engineering, but nonetheless, this is what it's known as here. The number of such states with the same eigenvalue is called the degeneracy of that state. So if there were 3 states all corresponding to the same eigenvalue, the degeneracy of that state would be 3. We'll come to this concept soon enough, as I said, although we have not yet encountered it in this particular problem. Another useful aspect of solutions to such a symmetric problem as this is what's called parity. These eigenfunctions that we see here have very definite symmetry. So we start at 0 over here and we go back down to 0 at the other side. And this function here has a very definite symmetry to it. And specifically, this n equals 1 eigenfunction is the mirror image on the left of what it is on the right. So if we take a point here on the right, then at the corresponding mirror image point on the left of this center line here, we'll get exactly the same value. Such a function is said to have even parity with respect to this point, to this axis, or it could be said to be an even function. Note, incidentally, that the n equals 3 function is also even though it goes below the axis here and above the axis there. It's still true that if you take any point on the right, then the corresponding point, the mirror image point on the left of this line, has exactly the same value of the function. The n equals 2 eigenfunction is an inverted image of itself. So whatever was the value on the right-hand side here, at the corresponding mirror image point on the left-hand side, we have the opposite value, minus that value. So the value at any point on the right of center is exactly minus the value of the mirror image point on the left of the center. Such a function is said to have odd parity, or to be an odd function. For this particular symmetric well problem, note that it is a very symmetric kind of a problem. It's exactly the same potential on the left as it is on the right in a mirror image sense. The functions, the eigenfunctions here, alternate between being even and odd and even. And all of the solutions of this particular problem are either even or odd. That is, all the solutions of this particular problem have a definite parity. And that kind of definiteness of parity of functions is quite common in symmetric problems. If we looked at an asymmetric problem, for example, if we tilted this potential here, we would find that the functions did not have definite parities. But a large number of at least idealized problems do have very good symmetry in them, and this parity tends to show up. And it is mathematically very helpful. For example, lots of integrals vanish exactly just because of the parity, and we don't even have to work them out.
Of course, perhaps the most remarkable thing about these solutions to this problem is the emergence of what we think of as quantum behavior. We started out by noting that electrons behave like propagating waves. We constructed a simple wave equation that could describe such effects for monochromatic and here monoenergetic electrons. Now we find that if we continue with this equation that assumes that the particle has a well-defined energy and put that particle in a box, then we found we got discrete values of that energy. Only discrete values of that energy are possible. And each of those has a specific wave function associated with it. This is the first truly quantum behavior we have seen with quantum steps in energy between the different allowed states. Let's look at the various differences and surprises we're seeing here.
So, specifically then, for this particle-in-a-box behavior, it's very different from the classical case in several specific ways. First of all, there is only a discrete set of possible values for the energy. And secondly, there is a minimum possible energy for the particle, here corresponding to the n=1 case. And that energy is the formula we have here. And note that there is no way of getting below this energy, and this energy is sometimes called a zero-point energy. And it comes about because of the quantum confinement we are doing. Note that if you make Lz smaller, this energy here gets larger. So this zero-point energy here is a consequence of the fact that we're confining this quantum mechanical particle into smaller dimensions to get larger zero-point energies here. It emerges because we're confining to small dimensions. It's a very quantum mechanical effect, and it's extremely common in quantum mechanics. So an unusual concept that does not really have an analog in classical mechanics. Thirdly, the particle is not uniformly distributed over the box. In classical mechanics, how would we think about a problem like this? Well, maybe we would think if the particle has energy that it is indeed bouncing back and forwards inside the box. But classically there would be no wave interference, and hence we would not have the phenomenon we have here of the particle having different distributions for different energies and indeed having any distribution at all. It would be nearly impossible to find the particle quantum mechanically near to the walls of the box, for example. That's not something we would expect from classical physics. And the probability here actually obeys a standing wave pattern. It's the square of these functions here. It's always positive, of course, the probability density. And that again is completely unlike anything we would have expected from classical physics. For example, in the lowest state, n=1, the particle is actually most likely to be found in the middle of the box. In higher states, there are points where we would never expect to find the particle. Strangely enough, for example, in the second state, you will almost never find the particle near to the middle of the box. This is, again, completely unlike anything we would expect classically. Note, incidentally, that each successive higher eigen state here, and each time we're just conveniently choosing these dashed lines, which are the eigenenergies, to be the zeros for the graphs that we use for the wave functions, of course. These points here are all zeros of the function, and we note that in the lowest function, we might say there are zeros on the walls, but there's no zero in the middle. In the second function, we have 1 0 somewhere in the middle of the well. In the third function, we have 2 zeros somewhere in the middle of the well. This, again, is a very common behavior in quantum mechanics. Finally, then, let's look at some of the energies that we see from using this problem as an example. Before we actually calculate some energies, let's talk a little bit about the units we're going to use. In quantum mechanical calculations, as in any branch of physics, we can always use joules as the units of energy, and sometimes we will do that. But these are rather large units, and instead we very often use the more convenient energy unit, one that has a simple physical significance, which is the energy unit of the electron volt. Now, approximately speaking, that's 1.602 times 10 to the minus 19 joules. And what that is it's the energy change of an electron if you were to move it through a potential of 1 volt, through an electrostatic potential of 1 volt. And we're just talking about the magnitude of the energy change here. So this unit here is a positive energy. And of course, where this 1.602 times 10 to the minus 19 comes from is it comes from the value of the electronic charge. And specifically, the energy in electron volts would be the energy in joules divided by the magnitude of the electronic charge. And more specifically, that's not just 1.602. To the best accuracy to which we know it, it would be this number here. The electronic charge, of course, is something that's in coulombs. So this energy in electron volts would be the energy in joules divided just by the number corresponding to the magnitude of the electronic charge. And as I said, this is a rather convenient unit because it corresponds to energies that we actually would see in working with atoms and things like that. So let's look at some orders of magnitude of what we would calculate for some sort of particle-in-a-box problem. Let's suppose that we confine an electron in a box that is half a nanometer or 5 angstroms thick. This is about the characteristic size of a small atom, like a hydrogen atom. So in this calculation then, here's our formula that we would put in with our distance Lz in here as 0.5 nanometers or 5 angstroms. If you work this out, this comes to 2.4 times 10 to the minus 19 joules, which is about 1.5 electron volts. And the separation between the first and the second allowed energies, E2 minus E1, would be 3 times E1. Remember, if this is 1 unit, then this one is 4 units of energy. And that would be about 4.5 electron volts, which is indeed a characteristic size of major energy separations between levels in an atom. They're of this rough magnitude here. So our particle-in-a-box problem, although we're not pretending that it's an accurate model of an electron in an atom, does in fact give us the right kind of magnitude of results, even in this very simple kind of model.
So now, with this simple particle-in-a-box problem, we've seen many of the novel and unusual aspects of quantum mechanics. Remember, we originally started out with the simple presumption that the electron behaves in some way like a wave, with de Broglie's hypothesis giving us the wavelength. We then took the simple and well-known Helmholtz wave equation, which we've seen many times in classical physics, as a starting point, and constructed the time-independent Schrödinger equation as a result. Here we've applied that to a very simple case. Presuming that our particle has to be within our infinitely deep potential well, we therefore presumed the wave functions had to hit 0 at the walls. That gave us the boundary conditions we need to solve our Schrödinger equation, and that led us to several surprising results. First, we only found solutions for very specific values of the energy, and we call those values the eigenvalues of the problem, specifically the energy eigenvalues in this case, or we might just say eigenenergies for short. This is the idea of quantization that is so characteristic of quantum mechanics. Additionally, we found this very bizarre phenomenon of zero-point energy. There's a minimum energy the particle can have, and it gets larger as we make the box smaller, and it's not the energy at the bottom of the box. Then we find there are different wave functions associated with these eigenenergies. Wave functions that are mathematically identical to the standing waves on a string tied to 2 walls, or like our guitar string. We call those wave functions the eigenfunctions of the problem. With our interpretation that the modulus squared of the wave function represents the probability of finding the particle at a point, we find behavior quite unlike the classical case. There is, for example, essentially no probability of finding the particle near the walls of the box. And we can also find other places in the middle of the box, for example in this state here, where there's similarly little or no probability of finding the particle. It can't be in the middle of the box when the wave function looks like that. All of this behavior is quite different from our classical expectations. Despite this being mathematically such a simple example, not only is it showing us many behaviors we get in more complicated problems, it also gives us the right kind of order of magnitude of results for energies and size scales of atoms. There are yet more aspects of quantum mechanics and its mathematics that are illustrated by this problem, and we will go on to those in the next section.